Now friends, we are in the third quarter wherein we are going to deal with reformulation of Faraday's law. That is, we are going to establish integral form of Faraday's law of electromagnetic induction. For this purpose, we are going to consider a single loop wire of any shape for that matter, but the contour has to be closed for the purpose. And let us suppose that at a given point of time, say t1, it occupies position say C1. Now let us suppose that this loop moves in magnetic field of flux density B bar with uniform velocity V bar. And out of that motion, at a later point of time, say t1 plus dt, where dt is infinitesimal small countable time, the coil is displaced through distance v bar dt, acquiring new position C2. Here we are considering elementary conductor dl bar displaced through distance, or rather displacement v bar dt. So the geometry of the closed loop is represented by dl bar. So here you can visualize a loop making an almost closed contour, and the story that we are considering here is in the presence of uniform magnetic field B bar, which we are presuming. Now this single loop coil is displaced in the space, and we are charting the movement of the slide as appearing in the animation. Here this closed loop represented by dl bar is infinitesimal small vector version of the coil, and the entire coil is spread over like this. The position is being represented by C1, and it is displaced with velocity v bar in this direction, and in time dt it travels v bar dt displacement and acquires new position C2. And here we are interested in the vector area, which is region of this strip kind of geometry. So vector area will be obviously cross product of this vector dl bar and the another displacement vector v bar dt. So v bar dt cross dl bar represents ds bar vector element. This is the area swept by conductor dl bar. Here we are yet to consider the complete conductor. We have presumed only a small elemental piece of conductor, and by virtue of that we are considering only the limited area which is part of the strip. Now we are considering B bar to be density of flux, and through the surface we have considered as area swept. We are cutting the flux, which can be accounted from definition of density of flux to be B bar dot ds bar. This is d phi, that is the flux cut. So d phi will be d phi leaving the complete ribbon shaped closed area can be obtained by operating double integration over the surface B bar dot ds bar, where ds bar is to be presumed from this formula. Now when we are displacing a single turn coil from position C1 to C2, the flux cut d phi will be double integration B bar dot ds bar. First integration we have to operate over dt, and second we have to operate over length of the conductor. So by substituting ds bar from this equation, we can write B bar dot V bar dt cross dl bar. So here dt and dl are the two variables on which integration is to be performed, and dt integration is to be performed for some countable time which will roll from 0 to t, and dl bar we have considered the conductor in closed loop. So the second integration, inner integration, has to be performed over a closed loop, and that is represented by variable dl bar. Now the integration over closed contour can be represented by integration over a circle, that is integration over closed loop. And what operation we are performing here is we are differentiating this equation on both sides with respect to time. So on left hand we have d phi by dt, and differentiation with respect to time and integration with respect to time will nullify the effect, and we are left with integration over closed loop b bar dot v bar cross dl bar. Now b bar dot v bar cross dl bar can be written as minus v bar cross b bar dot dl bar. This is a property of STP, that is scalar triple product, and thus we can write d phi by dt is equal to minus v bar cross b bar dot dl bar. So here v bar cross dl bar is a quantity of interest which is induced electric field inside the conductor, and normal consideration offers us E bar is equal to V bar cross B bar, and here minus sign we are taking on left hand side, so that we have minus d phi by dt is equal to line integration along closed contour E bar dot dl bar. This is nothing but the induced EMF. So this portion minus d phi by dt is the differential version of Faraday's law, which is representing induced EMF, and on right hand side we have line integration along closed loop E bar dot dl bar. This also represents induced EMF in the circuit. Now friends, we are going to rush through a video which is available on YouTube, and that resembles with the experimentation that Michael Faraday has carried out. So here we have a current meter, ampere meter, DC current can be measured. We have a single turn loop, then this is a 10 loop coil, and this is 100 loop coil. So here we can measure the current, and current through single turn coil, 10 turn coil and 100 turn coil. So here we have a bar magnet, and this coil is connected to the current meter, and when we bring the bar magnet near to the coil, it shows small deflection. You can observe small deflection in the current meter. So if you change the polarity, the direction of the kick observed in the current meter changes. Now let us see more significant effect with a coil of 10 turns, and that is now connected to a current meter, and we have a bar magnet with S pole that is cutting the flux. If you do it slowly, the fluctuation will be small. If you do it fast, the fluctuation will be more. So 10 turn coil has increased the effect, you can observe. Now instead, if we remove the magnet quickly, the kick is offered on the opposite side. Now let us do this same experimentation with 100 turn coil. So this is a coated coil, and the two ends are cleaned and connected to the current meter, and when you take a magnet near with high speed, it shows a kick. When you remove it, it goes in the opposite direction and so on. So this is how the induced EMF is developed in the circuit. Now the current in the circuit is directly proportional to the number of turns of the coil. This is what we have found experimentally. Then the current in the circuit is directly proportional to d phi by dt, that is rate of change of flux. If you do that action faster, the current is more, and it is inversely proportional to the resistance of the coil. Higher the resistance, lower will be the current, and the direction of induced EMF and hence current is opposite to the rate of, it opposes to the cause it produces, which is in form of Lenz's law. So R into I we can write as induced EMF equal to minus N times d phi by dt. Now friends, we shall go through a checkpoint, that is a numerical, to make our learning complete. Wire of length 200 cm held perpendicular to xy plane is moved with velocity v bar equal to 2 I cap plus 3 j cap meters per second through a region of uniform magnetic induction b bar equal to j cap plus twice k cap Weber per meter square. Calculate the induced electric field developed in the wire and induced EMF across two ends. So whenever we want to attempt a problem, we should write given things, and the moment we write given things, we have to realize whether they are in common system of representation or not. I mean MKS system or CGS system. So MKS system we call system international, and length of the conductor, which is straight parallel to z-axis perpendicular to xy plane, is 200 cm, means 2 meters. Velocity elements are 230 meter per second, and magnetic flux density is 012. So Weber per meter square. Now what all we have to find is E bar induced. Here even it appears as E bar, we are talking about induced E bar, and then we have to find induced EMF across two ends of this 2 meter long conductor. Now E bar induced is equal to minus V bar cross B bar. This formula we have to explore, and then we have to explore the integral version of Faraday's law. So herein we have induced EMF E is equal to V bar cross B bar dot dl bar, where the integration rolls over from initial point to final point. So solving that is very simple in terms. When you write V bar cross B bar with a minus sign in form of determinant, you can work out the vector concerning that, and E bar induced will be minus inside bracket 6 I cap minus 4 j cap plus 2 k cap. Here you can take 2 common if you like. Then the induced EMF across two ends, E is equal to integration E bar dot dl bar. So here E bar induced and E bar, they are opposite, and I want to mention that this E bar will be equal to minus E bar induced. Both are vectors, they are in opposite direction. Now we can substitute this quantity without minus sign, so it should start from here. So 2 is common, 3i minus 2j plus k dot, this dl bar is along z axis perpendicular to xy plane, means dz into k cap can be its representation. So k dot k will be 1, other dot products are 0, and we are left with 2z. Integration dz will be z, and z is rolling from 0 to 2, upper limit minus lower limit. We are left with 2 into 2, that is 4 volts.